So much also for the invitation. So today I'm going to try to show you how we can synthesize and functionalize strain rings. So if you are looking at the classification of Nathanson and Taylor about the most present cycle in drones on the market, the benzene ring is the substituent number 1, which is represented in here. And after you have 6-membered ring heterocycle with a nitrogen or an oxygen, 5-membered ring also with a nitrogen, and at the 10th position, you have a strain ring, the cyclopropane. It's very far away compared to the number of substituents present in a drug. But this kind of strain ring are very important. In fact, if you have a benzene ring in the molecule, you can be in front of problem of solubility, bioavailability, toxicity, and planarity. And in fact, medicinal chemist has shown that if you are increasing the sp3 number in molecules, you can have a better chance to have a compounds on the market. So what is FsP3? Is the number of carbon, sp3, towards total number of carbons. So what does this mean? Well, it means that you have to escape from flatland. And a way of escaping from flatland is to replace a phenyl ring by a cyclopropane, for example. And in this kind of compound, which is an anticoagulant, if you are replacing the phenyl ring in here by a cyclopropane, you have the activity that is multiplied by 5. But you have some other strain ring that you can replace, that you can replace the phenyl ring by other strain rings, such as a cubane, a cyclobutane, adamantane, or this bicyclopentane. And for example, for this compound, which is a gamma secretase inhibitor, which can be used in the Alzheimer's disease, if you are replacing this phenyl ring by this bicyclopentane, you can also increase the biological activity. So, I mean, for our part, we were interested in the synthesis of this cyclopropane having an amino acid or an amino ester at this position. As this kind of structure are present in a great diversity of bioactive compounds, such as, for example, the boceprevir, which is an HDC protease inhibitor. This one also, which is an HDC protease inhibitor, you can recognize this kind of structure at this position, or in this product in here, which is an anxiolytic, where you have also this cyclopropane having an amino acid at this position. So how can we synthesize this compound, which has 3 stereogenic centers that has to be controlled? Well, we have envisaged to synthesize this kind of cyclopropane, either with an hydroxy group in here or an amine. If you have an hydroxy group, for example, you can replace this hydroxy group by an amine by using a Mitsunobu reaction. If you this product should be obtained by the reduction of the cyclopropane having an exocyclic double bond. And this product should be obtained by a 3,3 sigmatropic rearrangement applied on the cyclopropane having a double bond, which is Z at this position. And you can, if you have the control of the stereogenic center, probably you can control these 2 other stereogenic centers, because this 3,3 sigmatropic rearrangement is done by this transition state, a chair transition state, which is represented in here. If you want to have a very good control of the stereogenic center, you have to control the stereoselectivity of the configuration of this double bond. So now, how can we synthesize this product? Well, from this glycolate or glycinate, which are represented in here. And this product should be obtained from this tribromocyclopropane. So we try to transform this tribromocyclopropane to this glycolate and glycinate. So at first, we have treated this tribromocyclopropane by n-butyl lithium, 2 equivalents, and then we have the formation of this intermediate that can be reacting with this aldehyde to lead to the formation of this allylic alcohol. Now, if you are doing an esterification with this carboxylic acid, you get the formation of the corresponding ester. Now we have to transform this compound to this intermediate that will be the precursor of this cyclopropane having an exocyclic double bond. So for doing this, we have treated this cyclopropene by KHMDS in the presence of TMSCl. Probably you have the formation of this cyclopropane having this double bonding here with the Z configuration due to the presence of these two oxygen that can do the complexation of the potassium. Now, having this intermediate, we raise the temperature and treat it by HCl and then by this diazomethane. And we got the formation of this cyclopropane having this exocyclic double bond due a 3,3 sigma-tropic rearrangement, and we have the control of these two stereogenic centers. Now, if we have, for example, an optically active cyclopropane having the configuration of this stereogenic center with this product as an EE of 88%. If you are treating this product under the same condition as previously, KHMDS, TMSCl, and then you raise the temperature from -78 to room temperature, treatment of the reaction media with HCl, and then by using TMS diazomethane, you get the formation of the desired compound with the control of these two stereogenic center and via this kind of intermediate as previously. Now, you can see that you have a very good transfer of chirality. If you are starting from a compound with an enantiomeric excess of 88%, you get an enantiomeric excess of 87% from this cyclopropane. The reaction is very general. You can have different R group at this position or on the cyclopropene. And if you have, for example, an alkyl side chain in here with a benzyl group, you get the formation of the desired cyclopropane. You get also a side chain with the tip groups, and also the reaction is pretty good. You can have an aromatic, a phenyl, an hetero aromatic, such as a pyridine, and the yield are also very good. You can have different substituents on the cyclopropene, such as an ester, diester group. The yield is around 57% for this alkyl side chain. And if you have hydrogen, you have a yield of 94%. So now, if we want to have the saturated cyclopropane, you have to reduce this double bonding here. So if you are the hydroxy, which is protected at this position, if you are doing the hydrogenation in the presence of a rhodium catalyst on carbon, you get the formation of this product where you have this stereogenic center, which is seen to the cyclopropane, and the hydrogen are in an empty position. And these two are cis. Now, if you are doing the deprotection of this alcohol by using DDQ, you need to use this catalyst in order to do the reduction, the iridium catalyst in methylene chloride, and you get the formation of the trans cyclopropane. You can see that the ratio trans-cis is pretty good. It's up to 96 to 4. So, I mean, we were able to obtain the formation of this kind of compound in here from this cyclopropane by using a 3,3 sigma-tropic rearrangement followed by a reduction. But now, if you want to have the formation of the amine, you have to deprotect this hydroxy group and then to do a Mitsunobu reaction in order to get the formation of this amino ester. This is possible. But now, if you want to have the other diastereoisomer, which is represented in here, what can you do? Well, maybe to start not from a glycolate, but from a glycinate, where you have an amino group at this position. And probably by using a 3,3 sigma-tropic rearrangement, you will get the formation of this cyclopropane with the control of these two stereogenic center. And after the protection of the nitrogen, the reduction of the double bond and the protection of the nitrogen, you will get access to this cyclopropane having this configuration at this position. So we have prepared this cyclopropene having, for example, this protected amine by a Bock group. If you are treating this compound by TMSCl and in the presence of LEHMDS, 4 equivalents at -78, you get the formation probably of this intermediate. And if you are raising the temperature, you have the 3,3 sigmatropic rearrangement that lead to the formation of this cyclopropene having this exocyclic double bond. After hydrolysis and treatment with the diazomethane, you get the formation of this amino ester, which is protected by the nitrogen is protected by a Bohr group. The yields are pretty good. If you have alkyl side chain in here or a phenyl group, you can see that the yield in the formation of this product is pretty good, and the diastereoselectivity is excellent. Now, of course, if you want to have the formation of this amino ester from this compound that we have synthesized previously, you have to cleave this Bohr group. So at first, we treated this compound by TFA. We got only the monoday protection. And if we wanted to have the cleavage of this Bohr group, we used TMS O-triflate, and then after hydrogenation, we got the formation of this amino cyclopropane with a good control of these 3 stereogenic centers. And the yield is not too bad, 98%. So, I mean, we were able to obtain this kind of cyclopropane, but we were thinking about to have the introduction of the cyclopropane by another way. And the other way that we have envisaged was a cross-coupling reaction in between an electrophile and a nucleophile in the presence of a transition metal in order to get the formation of this substituted cyclopropane. But the reaction has to be robust, chemoselective, easy to handle, transposable to a process, and we had to use a cheap catalyst. So we did a screening of transition metal in order to see if we can get the formation of this substituted cyclopropane. And the best conditions that we found were the following. If you are using an alkyl iodide in the presence of the cyclopropyl Grignard, cobalt 3.5 mol%, in the presence of TMADA, which is represented in here in THF, we got the formation of the coupling product. The reaction is very general. You can introduce, for example, this alkyl side chain with a phenyl group, which the yield is around 84%. Another side chain that you can introduce from the iodide, where the hydroxy group is protected by a benzene group, you can have a yield of 85%. You can have also an alcohol, which is protected by a TBDPS group. The reaction is very chemoselective. You can introduce, for example, this group in here, where you have an ester, and you can see that the ester is still in place, even if you are using a Grignard, and the yield is around 55%. You can introduce a side chain with a nitrile. The yield is not really good, but if you are introducing, for example, a GEM dimethyl group at this position, the yield is increased to 81%. And in fact, the GEM dimethyl group can protect the cyano group, which is present at this position. You can introduce, for example, a side chain with an aromatic group with a bromide. And you can see that the reaction is chemoselective. The yield in this compound is 78%. Of course, you can do other coupling reaction as you have a bromide, which is present at this position. You can also introduce this cyclopropane on heteroaromatic, heterocyclic compounds, such as, for example, if you are using this iodopiperidine, you can have the piperidine with a cyclopropane at the 4th position. The yield is pretty good also. And more challenging is this piperidine with a 3 iodo group at this position. Here also, the yield is pretty good. You can introduce the cyclopropane with the yield of 85%. And in fact, I'm sorry, you do not have the elimination of the iodide under this condition. With the pyridine, with the iodide, you can have also the formation of a pyridine with a cyclopropane, as well as with acetidine, you can have the formation of this product with a yield of 91%. So we can do this coupling reaction from a iodide in the presence of this Grignard and a cobalt a cobalt catalyst to get the formation of the coupling product. Now the question is it possible to get the formation of substituted cyclobutane from a iodide and a vinyl with a cyclobutyl grignard in the presence of a cobalt catalyst? And the answer is yes. You can use different alkyl iodide in here in the presence of this butyl grignard, cobalt attack, TMADA and THF at 0 degrees, and you can get the formation of the coupling product. Here also, you can introduce, for example, this alkyl side chain with a phenyl with a methoxy group. You can also introduce a cyclobutane onto this acetylene, and on the pyrrolidine, you can also introduce this cyclobutyl group. And here also, the yields are in between 60 to 80%. Now, the thing that we try to do is to introduce, for example, this bicyclic cyclopentane onto a iodoacetylene. And in fact, if you are treating this iodoacetylene by this grignard in the presence of always the same condition, cobalt attack and TMADA, we never observe the formation of this compound. So what can we do if we want really to have this product? Well, to screen other transition metal. And after screening, we saw that we can get the formation of this coupling product from this iodoacetylene and this bicyclopentane by using lithium coupled tetrachloride in THF, and under this condition, you get a yield of 57%. So, I mean, we can introduce different strain ring. Now, let's have a look at isoquinolone. Isoquinolone are important compound, and they can have very interesting biological properties, such as, for example, this compound, which is an antitumoral agent, which is an tyrase 1 inhibitor. This one also, which is also an antitumoral agent, and this one, which is an immunosuppressive agent. It is a tyrosine kinase inhibitor. And in fact, all these isoquinolone are possess an aromatic ring in here and an heterocycle at this position. What can we do if we want to increase the biological activity of such compound? Well, maybe to replace the phenyl ring by a cyclobutane. So it's very nice to have this kind of idea, but now how can we synthesize these compounds? Well, we have envisaged to synthesize this kind of bicyclic compound having a cyclobutane from this cyclobutanyl hydroxamate and an acetylenic in the presence of a metal catalyst by doing a CH activation of a cyclobutane. So the hypothesis was that if we are treating this compound by a metal in the presence of a base, probably we will have a concerted metallation deprotonation step that will lead to the formation of this intermediate. And if you have an acetylenic in the reaction media, you will have this metal in here that will complex this acetylenic, and then after carbometallation, we will have the formation of this intermediate, this 7-mandarin intermediate. And then after reductive elimination and cleavage of this NOR bond, you will have the formation of this bicyclic compound, regeneration of the metal and the base. So we tried to do this reaction, but we were aware that it was not so obvious. There are some challenges. For example, this activation of a CH bond, CSP2 CH bond, is pretty challenging. It's a vinylic one and it's pretty challenging. The other thing is that you have an electron withdrawing group. So if you have nucleophile in the reaction media, you can have a Michael addition. And you can have, if you have this transition state, you have this 4-man between. So it is a strain metallocycle at first, but also the cyclobutane can also open. So there were some challenges in here. Anyway, we tried to do the reaction from a cyclobutanyl hydroxamate in an intermolecular reaction. So we have synthesized this compound, treated this compound by this acetylenic in the presence of a rhodium catalyst, a base, in a solvent such as methanol, chloroform, DMF, DCA. And we have the total conversion of the starting material, but we never observe the formation of the bicyclic compound. So what is happening in this kind of transformation? Well, it's an intermolecular reaction. So maybe we will have a better chance to have this reaction to work in an intramolecular reaction. So we prepare this kind of hydroxamate in here and treated this hydroxamate in the presence of a rhodium catalyst and a base in order to see if we can get the formation of this kind of bicyclic compound. So we prepare different compounds of this type, treated this compound by the rhodium catalyst and cesium acetate in methanol, and we observe the formation of the desired compound with with good yield. For example, if we have, for example, a phenyl group at this position, the yield in this bicyclic compound is around 64%. You can have a phenyl with a bromide in the para position, a methoxy in the para position. You can see that the yields are similar, around 80%. For this one, with a methoxy in the ortho position, the yield is only 44%, due probably to steric hindrance. And here we have to force the condition. Instead of 5 mol%, we need to use 10 mol% and 1 equivalent of a base. You can introduce also heterocycles, such as a pyridine, but the pyridine has to be protected by a chloride. Otherwise, the reaction is not working because you have the basic nitrogen, the cat complex, the catalyst. You can have also different R group at this position, such as a TMS or a methyl group. Here you can see that the yield are good to modest, and you can have different size of this tether in here. For example, you can have 1, 2, or 3 carbon at this position, and you can see that the yield are pretty good too. You can also have the substituent on the cyclobutene, and for example, if you have an isopropyl or a benzyl, you can have the yield in this compound, which are around 80%. So we have prepared this kind of isoquinolone, kind of isoquinolone, by replacing the aromatic group by a cyclobutane. And in fact, the thing that is happening is also that with straining are okay, but macrocyclic compounds are also very fine to have a biological activity. And to my opinion, this kind of macrocyclic compound are underexploited class of compounds. You have only 2% of these macrocycles on the market compared to the non-macrocyclic compounds. And in fact, if you have, for example, this product in here, which is a farnesyl transferase inhibitor with an antitumor activity, you can see that the EC50 is around 5,000 nanomolar. But if you have the closed form, the EC50 is 0.1 nanomolar, so much more active. Now, a second example, if you have this product in here, open form, which is a checkpoint kinase 1 inhibitor, which is a chemosynthesizing product, you can see that the EC50 is around 4,000 nanomolar. And if you have the closed form that was synthesized by using a ring closing metathesis reaction, the EC50 is 10 nanomolar. So, if you are considering again this isoquinolone, is it possible to increase the biological activity of this compound if you are synthesizing isoquinolone with a macrocycle of this type? So now, as I said previously, we have this kind of a hypothesis. How can we access to this macrocyclic isoquinolone? Well, maybe as previously, by CH activation. Maybe this macrocyclic isoquinolone should come in from this hydroxamate in here by a CH activation, and this hydroxamate will have this triple bond in here that will lead to the formation of this macrocycle and the construction of this heterocycle. So the hypothesis was that if we were treating this compound by a metal in the presence of a base, we will have a concerted metallation deprotonation reaction that will lead to the formation of this intermediate, and then this metal can complex this acetylenic that will lead to the formation of this intermediate. Now, after carbonmetallation, we will have the formation of this metallus heterocycle, which after reductive elimination and cleavage of the NO methoxybond will lead to the formation of this macrocyclic compound, regeneration of the catalyst, and also regeneration of the base. Now, the first compound we have examined was this one, which has this product, which this has this ether group at this position, because we know that this can force the macrocyclization. So we have treated this compound by a ruthenium catalyst, which is represented in here, in the presence of a base and an additive in the solvent, and we observe the formation of the desired compound. The reaction has been done in water at first. The yield was not really good, 14%. Now, if you have chloroform, the yield is increased to 41%. In water, the product was not really soluble. So in chloroform, the yield was a little bit increased. We say, okay, we are not using very high dilution. So maybe one trick to have high dilution is to do a slow addition of this compound onto a solution of the ruthenium catalyst. The yield was a little bit increased, but it was not really great. But the students made a very important observation. He saw that after 15 minutes, even after the slow addition, the reaction was stopped. So what does this mean? In fact, that means that the ruthenium catalyst was not regenerated in the reaction media. So we need to add an additive. And the additive that he has added was copper acetate. Under this condition, chloroform, in the presence of the ruthenium catalyst and the copper acetate, you obtain a yield of 85%. The reaction is very general. As you can see, you can have different aryl group at this position. For example, a cyano, a bromo, a methoxy, a carbamate. The yields are pretty good. You can have also a substituent on the ortho position, methoxy, chloro, nitro. The yield is around 80% or so. And you can have alkyl at this position or olefin, and your yield is around 72%. Now, we have seen, as I say, this tether in here can induce the macrocyclization in order to get the formation of this isoquinolone. But is it really necessary to have such a linker in order to have the formation of this product? And the answer is no. You can have, for example, only 2 oxygen in here, and you can have the formation of a 12-member ring, a 13-member ring, a 20-member ring. You can have an oxygen or a nitrogen, which is protected in here. You can have a 12-member ring. You can have an ester with an oxygen. You can have a 14 and a 15-member ring, or you can have an amide in here. And we can have the formation of this macrocyclic compound, which is a 15-member ring. Here, the yield is not really good because the starting material is not really soluble under this condition. I have to point out that we can work on a larger scale, 1.3 grams, and we can get the formation of this compound with a yield of 58%. So the thing that I try to show you is that we can have the functionalization of a cyclopropane by using a sigma 3,3 sigmatropic rearrangement applied on glycolate and glycinate in order to get the formation of the cyclopropyl having an exocyclic double bond that can be transformed to this amino ester having a cyclopropane in the alpha position. We can have also this substituted cyclopropane or cyclobutane by doing a cross-coupling reaction in between a iodide and a Grignard in the presence of a cobalt catalyst. If you want to introduce this bicyclopentane, you have to use a copper catalyst in order to do the coupling reaction. And you can have the formation of this kind of this heterocyclic, bicyclic heterocyclic with a strain ring from this hydroxamate. And you can have also the formation of macrocyclic isoquinolone by doing a CH activation applied onto this hydroxamate by using rhodium and ruthenium. Now, the thing that I would like to do is to thank all my group for the dedicated work. And I would like to thank Christophe Meyer, Guillaume Ernouf, who were working on this cyclopropane having an amino ester, Thomas Saeg, who was working on the formation of this heterocycle with a cyclobutyl group, Jean-Philippe Krieger, who was working onto the macrocyclization, Amandine Guéridon and Claire Anderson were working on the coupling reaction. I would like also to thank the SPCE, the CNRS, Divershin and Sanofi, who are two French companies, for the financial support. And I would like to thank you for your kind attention. Thank you so much.